Now we're going to start a new phase in our lessons. But before that, let's go ahead and get our joke today. And it might not make sense till the end of the lesson. The ends justify the means. And we're going to be looking at averages of samples and how n plays into that. So first of all, let's go ahead and review some terms because now, before we've been working with populations, and remember a parameter is a numerical descriptive measure of a population. So we've been working primarily with that. Now, a sample statistic is a numerical descriptive measure of a sample. So we're going to actually look at populations of samples. That's the twist, which leads us to statistical inference, which is a conclusion about the value of a population parameter based on the information in the corresponding sample statistic and the associated probability distributions. So we're looking at what's called sampling distributions, and this is a probability distribution for a sample statistic. So that probably went a little over your head, but as we go through the examples, we'll kind of refresh it and talk about it. So first, let's go ahead and we have populations. Let's take a look at this population that is normally distributed. You can tell it's symmetric, mound-shaped, all right? And if I were to take samples of size 2, so there's the sample, there's the average, here's another sample and that average, there's that sample and that average. So I'm taking multiple samples of size 2. What will the averages look like after if I do this for lots and lots and lots of samples? Well, you can see it looks like a normal distribution. The mean looks the same. The only difference is the width here. It's narrower. And that kind of makes sense because the probability of getting two really low values is not real high here. So it tends to condense it. The variance in the standard deviation gets smaller. All right, let's go ahead and look at a larger sample size 10. So here you can go, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's your average. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Almost there. There's your average. So what's going to happen when I do lots and lots of samples of size 10? You're going to find out that you're going to get a normal distribution again, like your population, but it's even narrower now with this larger sample size. Let's do one more with sample size 25. And here we got to go, and I actually do quite a few samples here. There's 25 points almost. And let's see, there's the average of 25. And we basically, now I just speed it up. And if we do lots and lots and lots and lots of samples, we see that this looks a lot like that. The mean's the same, but it's a much narrower distribution because the probability you're going to get all of your 25 on the low end or all of your 25 on the high end is very low. Okay, so if we draw the different distributions, and I would prefer you do that in your notes, so you can see here's sample size 2, sample size 10, and sample size 25. So how do the means differ for the different ends? Well, the means seemed approximately normal, and so was our population. And the average means are roughly the same as our population. Good enough. We're going to say the means are the same, roughly. Now, what happens to the variance as n increases as I get larger sample size? The variance decreases. So we have our standard deviation is going to get smaller. Now, this was for normal distribution, so it kind of makes sense that if I have a mound shape, my means are going to be mound shaped. Is that true for all distributions? And the question is, will the means for this, if I take samples from here, also look uniform? So I'm doing samples of size 5. And there's my first, average, second, and I keep taking samples. Let's go ahead and speed it up here pretty quick. One more. And you notice I'm not getting very many in the super low end. I got this one, but I haven't got much in the high end either. And why is that? Because the probabilities of having everybody be down here or everybody be up here is pretty low. In fact, when I start taking lots and lots of samples, it looks pretty normal. Now we'll go ahead and do samples of size 25. So this over here, this is the graph of samples of size 5. And now we'll do samples of size 25. And then I'll go ahead and take another. And you can see already this average right here is very close to the mean of the population. And as I take more and more samples, I will also get a normal distribution, or what's approximately normal. And this time the variance or the standard deviation is much smaller. So even though I started with the uniform distribution, I still ended up with normal distributions or approximately normal distributions for the means. All right, so let's go ahead and look at a crazy distribution. And this one is a bimodal distribution. So I have a lot on the low end and a lot on the high end. So you would think it would be easier to get some high-end averages when I have a sample size of 2, and you would be right. And in fact, if I did lots and lots and lots of samples, I would eventually get with a distribution that looks something like this. All right. And if I increase this, so this looks like a trimodal, 3 peaks here, because this is sort of a crazy distribution. And if I did it with 5 samples of 5, then you can see I get that funny shape right there. And then if I go ahead and do samples of size 10, so when I had samples of size 2, I didn't get a normal distribution. When I had 5, I did. 10, I'm starting to get a little better. And now let's do samples of size 25. And you're going to see that actually with 25, all of a sudden we migrate from this crazy distributions here based on my crazy original distribution all the way to a normal or approximately normal distribution with large enough sample size. So first of all, 2 of the things we can conclude from our observations is that the average for our samples distribution is the same as the population distribution. You saw that the centers were pretty much the same every time, all right? Then we have this crazy Pythagorean theorem of standard deviation, and it's not so important that you follow this whole derivation. What you really need to understand is that when I'm looking at standard deviation of samples, not an individual in a sample, but of samples, then it's smaller, the spread is smaller, and I just divide this standard deviation for individuals by the square root of my sample size. So this brings up the central limit theorem. When n is sufficiently large, our guideline is 30. It tells us that the distribution of the means is approximately normal, even if the population is skewed, all right? The average for the sampling distribution is the same as the mean for the population. And the standard error of the averages is about square root of n times smaller than the population standard deviation. The way we calculate probabilities are the same, except you have a smaller standard deviation. So let's go ahead and look at an example of SAT scores. In 2017, the mean math SAT score was 527 with a standard deviation of 107. All right, so there's 527 and 107. Since the SAT is standardized and the graph at right is fairly symmetric, it's reasonable to assume that the population of SAT scores is approximately normal. So I can go ahead and, let's see if I can get back to my arrow options. Here we go. So I can go actually fill in this model. The mean is going to be the same, 527. And then I'm going to use that standard deviation to go up and to go down. So what is the probability that an individual student scores over 600 on the SAT? Well, looking at the picture, that doesn't look too bad. 600 is about here. I'd say, well, it's not half, but it's pretty high, all right? Probably at least 20%. So let's go ahead and calculate a z-score. I want you to practice being able to do that. Z-score is x, 600 in this case, minus my mean up there, divided by my standard deviation. And I get a z-score of 0.682. That makes sense because 600 is above average. Not a lot above average, but it is above average. Okay, and then to find the probability of getting a z-score over this in this area, I'm going to do normal CDF 0.682, 1,000, 0, 1, which gives me 0.248. Now, some of you like to use the x values on here when you're using the calculator, and that's okay. Just remember, you've got to know which one you're using. So for x is greater than 600, I can actually do normal CDF 600, but I don't want to do 1,000 anymore because that's kind of close to my 600. It's over here somewhere, right? I want to get far away because I'm trying to go as far to the right as I can. So I'm going to use 100,000. 10,000 probably would have worked. 527 and 107. It doesn't hurt to go extra large on this, okay? So your answer will be fine. So anyways, the probability that an individual student, one student in the population, scores over 600, so any individual, is almost 25%. All right, now we're going to take a random sample of 20 students and record their scores. Can we use a normal distribution even though n is less than 30? Of course, because our population is normal. If the population is normal, you can always use normal, or it's approximately normal anyways. What would the mean be for samples of size 20? It should be about the same because the means are the same. This is a super easy question. When they ask you the means for the sample, it's the same as the mean for the population, that 527. What is going to change is your standard deviation. It's not going to be 107 anymore. It's going to be 107 divided by the square root of 20, which happens to be about 23.9. So when I fill in the model, 527 is still in the center, but now I'm only jumping up by 23.09 instead of 107. So if you look at it, those numbers are smaller, all right? So that's my model. So what are the mean scores for the middle 95% of samples? Well, that's 2 standard deviations away using the empirical rule, which would be these 2 numbers right here. Okay? Now, what is the probability that the average score for our sample is over 600? So this is the average of all 20. So 527 is still here. 600, if you recall from the previous, let me go back. 600 is actually way over here. It's more than 3 sigma away, all right? So it's probably smaller. 600 is there. So I'm looking at a tiny probability. Let's go ahead and figure out the z-score. 600 minus 527. Notice I'm using a different standard deviation. Why? Because I'm looking at the average of samples, not an individual. And I get a standard deviation of 3.05. So the left boundary for this area is 3.05 on z-scores, and the right boundary is 1,000. So I'm going to do normal CDF 3.05 to 1,000, 0, 1. And I get 0.0011, so less than 1%, 0.11%, very low. If I want to do this probability with x values and skip the z-score, I can. Let me show you how to do that. It's 600, so I still have the 600. I still have a very large number here, still have my original mean, but my standard deviation is a little different. It's now 23.9. So that is, let me go ahead and highlight that again. Pointer highlighter. So this 23.9 is what's really different from the first time because our standard deviation is different. Okay, speeds of cars on a highway have a mean of 52, all right, and a standard deviation of 6. So can we draw, oh, and they're very likely to be skewed to the right, a few very fast drivers. By the way, the fastest I ever drove was 115 miles per hour approximately, and it was legal because I was on the Autobahn in Germany, and that was as fast as that little Volkswagen would go. All right, and I was still getting passed, by the way. Can we draw a model for the individual drivers? Why or why not? Well, we really can't because the population is skewed. But now let's take a random sample of 40 drivers. That's important to know. Can we draw a normal model for the average samples of 40 drivers? Why or why not? Yes, we can, because our sample size is greater than 30. Remember, our guideline is if it's greater than or equal to 30, doesn't matter what the population looks like. What would the mean be? That's an easy question. It's the same. It's 52 miles per hour. What would the standard deviation be for samples of size 40? It's going to be smaller by the square root of 40. So I'm going to take that 6 there and divide it by square root of 40, and I get 0.95. So if I fill out my model, you'll see that the spread is not very big, okay? Now let's go ahead and calculate what are the average mean speeds for the middle 99.7% of samples. Well, according to the empirical rule, that would be 3 standard deviations away, here and here, which gives me 49.15 to 54.85 miles per hour. Now let's do some probabilities. What is the probability that the average speed for our sample is less than 50 miles per hour? So I'm going to calculate a z-score for 50, get negative 2.105, and it's right about there. I want less, so it's this left piece. So the left boundary is way over here to the left. All right, pretend I can get over there. You can't really see my little highlighter right now. Pointer options. Arrow options, automatic. So the left is way over here somewhere, so we're going to say it's negative 1,000. And the right boundary is this negative 2.105. So I'm going to do normal CDF, negative 1,000, negative 2.105, with 0 and 1 because I'm using z-scores. And I get 0.0176. And I'll let you check it, see if you can get the same rough answer using x values. What is the probability that the average speed for our sample is between 50 and 55 miles per hour? Well, we already have the z-score for 50, which I'll go ahead and put in there. It's probably a little bit too much to the right. But I still need the z-score for 55, so I'll calculate that. And that goes over here. I'm looking at between, so that's this area. And I'm just going to do normal CDF. Z left is going to be negative 2.105. Z right is going to be 3.158. And I get 0.982%, or 0.982, which is about 98.2%, which kind of makes sense based on our picture. Remember, whenever you're stuck and you're getting the wrong answer, you can draw a quick curve. You don't need to be super accurate. Just draw a hump and make sure you're on the right side of the average, and then figure out where you're shading, and that will help you define what your left and your right numbers are.